So this skill is not a standard in itself, but it is a skill that we are going to need for future standards, and it will be needed in geometry and in Algebra 2 beyond this class. It's called simplifying radicals, and how we simplify radicals is using a process of prime factorization. In order to do that, we need to identify what is a number that is prime. So I have a list here of all the numbers from 1 to 100, and I've separated them out into 3 different groups. We have 1, which is neither prime nor composite, and then we have prime numbers and we have composite numbers. A prime number is a number that has exactly 2 factors, so it can only be divided by 1 in itself evenly. A composite number has more than 2 factors. It can be divided by 1 in itself and at least one other number. Take a moment to pause the video and make your chart look like mine so that all your prime numbers are identified. Now, just like fractions, our radicals or square roots need to be simplified. And we know that a square root is simplified if the number that's underneath that square root can't be divided by a number that's considered a perfect square. So a perfect square is made by multiplying a whole number by itself. So if we are taking a square root of a number and it's a perfect square, then that means we should be able to rewrite it to look something like this, a number squared. And when we square root a number squared, we end up with just the number, no square root anymore, and there's no square after it as well. So the square root of 25 is the same thing as saying the square root of 5 squared, and the square root of 5 squared is just 5. So prime factorization helps us find all of those pairs of factors, all of those something squareds, so that we can simplify our radical. Let's look at our example here. Now there's 2 different methods we're going to use. You may choose whichever method you'd like, and I'll alternate my notes so that you can see an example with both of them. To simplify the square root of 54, our first method is a factor tree. And with a factor tree, it has some positives and negatives. Positives are that you can divide whatever number you're trying to simplify or do your factor tree with by anything that goes into it. It doesn't matter if it's prime or composite. The downfall is that factor trees can get a little messy, and it can be hard to organize your numbers. So if you're a person that maybe has handwriting that goes all over the place, or it's difficult for you to find your numbers or to organize, and you like things in a more organized fashion, the factor tree may not be for you. To help you not lose numbers, though, you can circle your prime numbers as you create your tree so that you can find all your numbers later. So to do the square root of 54, we're going to do a factor tree for it. 2 numbers that multiply to be 54. We're going to use 9 and 6. Now 9 and 6, neither one is prime, so I don't circle them. But 9 can be divided into 3 times 3, and both of those are prime. That's why they have circles on them. 6 can be divided into 2 and 3, and both of those are prime. That's why we have circles on them. So 54 can be rewritten as 3 times 3 times 2 times 3. Now we're going to do the same thing. We're going to end up with the same numbers, but we're going to use a different method called the cake or the ladder method. And with this method, one of the downfalls is that you can only take out prime numbers when you're doing your cake or your ladder. But one of the benefits is that you can use your prime factorization chart to quickly find what numbers to check. And all of your prime numbers will be lined up. You don't have to go searching from them or remember to circle if it's prime. So there's some benefits and drawbacks to each one. So 54. I can't use 9 and 6 because neither one of those were prime. We have to look at our prime factorization chart, and my suggestion is always to start with the first prime number. So 54, can it be divided evenly by 2? And it can. 54 divided by 2 is 27. So 27, can it be divided by 2? Nope. So we'll look at the next prime number, 3. Can 27 be divided by 3? Yep. And I get 9. Can 9 be divided by 3? Yes. I get 3. Can 3 be divided by 3? Of course. And I get 1, which is why we call it the ladder method, because I make my little 1 into a stick figure, and he climbs the ladder. But all of my prime numbers are lined up to the left here. Notice I had 3 3s over here, 3 3s here, and a 2 and a 2. Same numbers, just different method. It does not matter which method you choose. You might also see the ladder method called the birthday cake method. That's just when we start the birthday cake down at the bottom. The same thing's happening. 54 divided by 2 is 27. 27 divided by 3 is 9. 9 divided by 3 is 3. 3 divided by 3 is 1. The difference is we're working our way up instead of working our way down. But you get the same process, same result. Now, what do we use with all these prime numbers that multiply to equal 54? Well, we are going to look for pairs. So I'm looking for 2 of the same number, which here I have it, 3 and 3, because I can rewrite 3 and 3 as 3 squared. There's no other pairs, so they just get written on their own. Now the benefit of writing it this way is now we can use the information we had up here. I can take the square root of something squared, and it comes outside of the radical. The square root of 3 squared is 3. And 3 and 2 don't have something squared, so they stay underneath the radical. 2 times 3 is 6. So the square root of 54 can be simplified to be 3 square roots of 6. Let's do some more practice. And I will alternate which method I'm using in case you like one method over another. So I'll do the first one with a factor tree. So here's 12. If I'm using a factor tree, I can choose whatever numbers I want as long as they multiply to be 12. So I'll use 3 and 4. Now 3 is prime, so I want to put a circle around it so I don't lose it. 4 is not prime, which means I need to separate it out more. 2 and 2. Both of those numbers are prime, so that's the end of my tree. I am looking for pairs. So I have 2 2's. So underneath my radical, I can put 2 squared, but I only have 1 3, so 3 will remain on its own. And when I simplify this, I have the square root of 2 squared is 2, and the square root of 3 remains inside. So square root of 12 is the same thing as 2 square roots of 3. I'll use the ladder for the next one. 48 is the number that I need to use the ladder for. Only prime numbers can come out if you're using the ladder. So I'm going to start with the first one that works, 2. 2 goes into 48 24 times. 2 goes into 24 12 times. 2 goes into 12 6 times. 2 goes into 6 3 times. And 3 is a prime number, so he comes out, leaving a 1 at the bottom. And remember, that's my 1 that I usually make into a little guy to climb the ladder. And we're looking for pairs here. So I have a pair of 2's. Here's another pair of 2's. So I have square root of 2 squared, square root of 2 squared, and 3. The square root of 2 squared is 2. The square root of 2 squared is 2. And 3 doesn't have a square, so he has to stay inside. 2 times 2 gives me 4. square root of 40. I'll go back to a factor tree for this one. All of these can be done with a factor tree, and all of these can be done with a ladder, whichever method makes the most sense to you. If you're using a different method than what I'm using in my notes, just check your numbers at the end and make sure that we have the same prime numbers. Any order, but the same prime numbers should be listed. So for 40, I'll use 4 and 10. Neither one of those are prime. 4 can be broken down into 2 and 2, and both of those are prime, so they get circles. 10 can be broken down into 2 and 5, and both of those are prime, so they get circles. I'm looking for pairs. I have 2 2's, so 2 squared, but then I have one little 2 left over and one 5 left over. The square root of 2 squared is 2, and I have a 2 and a 5 left over, so 2 times 5 gives me 10. How about 160? This time I'll use a ladder. A prime number that goes into 160 is 2, 80 times, 2, 40 times, 2 goes into 40, 20 times, 2 goes into 20, 10 times, 2 goes into 10, 5 times, and 5 is prime, so it comes out, leaving just a 1 at the bottom. We're looking for pairs. I have a pair of 2's and another pair of 2's. So inside of the radical will be 1 2 squared and another 2 squared. Then a 2 and a 5 are singletons. Square root of 2 squared is 2. The square root of 2 squared is 2. And 2 and 5 have to stay inside. 2 times 5 is 10. 2 times 2 outside of the radical gives me 4. So 4 square roots of 10 is the same thing as the square root of 160. $147. I'll use a factor tree for this one. So 147 divided by, we'll use 3, goes in 49 times. Now 3 is prime, so I'm going to circle it. 49 can be divided by into 7 and 7, which both of those are prime, so we'll circle them. Notice even though there's variables here, I started the same process for this one as I did all of the others. We are looking for pairs, and so I have the square root of, there's a pair of 7's, 7 squared, and a little 3 left over. Now it's time to deal with the variables. So I had x to the 5th. That means that I have 5 total x's. So I can pair them up just like I do numbers that repeat. There's a pair, there's a pair. So there's an x squared, and x times x, x squared. And there was 1x left over. Now we'll do the y's. Y to the 4th means that there are 4 y's. Pair them up, and I get y squared and y squared with none of them left over. Now let's do some square roots where we can. Square root of 7 squared is 7, but the 3 has to stay. Square root of x squared is x. Square root of x squared is x. And this x has to stay. Square root of y squared is y. Square root of y squared again, another y. So we'll simplify. 7, x times x is x squared. Y times y is y squared. And 3x remains. The last one, I'll use a ladder. I have 99. Prime number that goes into 99 is 3. And it goes in 11 times. 33 times. Prime number that goes into 33 is 3, and it goes in 11 times. 11 is prime, so it comes out leaving a 1 at the bottom. You can draw your little guy if you want to. I'm looking for pairs. So I have a pair of 3's underneath my radical and an 11 left over. And if I'm looking at the variables, y cubed means I have 3 y's, and I pair them up, y squared and 1 little y left over. It's time to simplify. Square root of 3 squared is 3, and 11 has to stay in. Square root of y squared is y, and this y has to stay in. So 3y square roots of 11y.